Hello and welcome to Foundations of Mathematics. Here's an outline of what we're going to talk about today. Start with the target audience and goals for the lecture. The idea here is to try to fill in a number of gaps that many people have in math. A lot of people learn math through rote, through memorization, but they never really develop an intuitive understanding of what math is all about and why you need it and why it's important and why it's fun and interesting. So this lecture is an attempt to add that sort of color to mathematics. It'll be useful for probably 10 years old and up, including adults. So a lot of adults, I think, struggle with math and don't really understand the basics simply because they were never taught. So some of this may be repetition for you, and some may be new. You may find some brand new ideas and concepts that really help you think about math in a new and fun, interesting, and kind of foundational way. So we're going to start by talking about a little bit in detail about what mathematics actually is, a little about human language, some pre-math, what are numbers, some information about larger numbers, base, and what base means and how it's relevant, significant digits, the law of large numbers, fraction notation, exponents, estimation using exponent notation, something about the numbers in the world around us, and why, then a couple of examples to sort of rehash things that all of us learned in elementary school. Why does addition work the way we were taught? And then a different way to think about subtraction. So first, what is mathematics? Interestingly, the thing about the word mathematics is it doesn't actually have a single generally accepted definition. A lot of people describe it in slightly different ways. So broadly, math involves the study of quantity, patterns, numbers, and sets. But it's broken down and refined in a lot of ways. Many agree that mathematics is actually a kind of science. I like to think of it at its core that math is really the science of measurement. This is a really important concept to grasp in helping you build a solid foundation for mathematics. I'll say it again, that math is the science of measurement. And we can measure things like distance, time, weight, money, speed, height, area, volume, shape, motion, structure, change, and a lot more around us. Math actually requires and rests on a strong philosophical base. Things like axioms, logic, theorems, deduction, induction, these are all used to form the foundation of mathematics, and they all required philosophy, and many actually had to be invented. Math actually uses its own language. You could even think of it as possibly more than one language. And this language of numbers and notation, there's a lot of depth to the notation used in math. So another way to think about math is that it's a tool to help us describe and think about the world around us in great detail. A high-level view of mathematics. Everything about math had to be discovered, even the underlying philosophy. Natural numbers, integers, zero, arithmetic, algebra, calculus, sets, and all of that had to be discovered. It's not just present out in the world for us to observe. Humans had to think about it, analyze it, condense it, conceptualize it, and turn it into a study and a process and a science. Which that also means, by the way, that math has a very rich and interesting history. I won't get into that too much in this lecture, but it's a fascinating subject, and I highly recommend it. Numbers are actually needed for math, but on the other hand, math is much more than just numbers. There are a bunch of subspecialties, entire deep areas of study, things like real analysis, set theory, number theory, statistics, geometry. Calculus would be part of real analysis. Each of these are fields that people who study math for a living specialize in. You can get a whole PhD in a very narrow subject area like this. Math is also an important enabler for most specialty sciences. I mean, can you imagine doing physics, chemistry, biology, engineering, and computers, for example, without math? It would be impossible. So having a solid foundation in math also helps build up a solid foundation for the specialty sciences. Talk about human language for a minute. For us, for humans, what are words? They represent concepts. Now, what are concepts? Concepts are condensations of knowledge. They're generalized in some ways and yet specific in others. For example, the concept table, the word table, represents an object with a flat surface and something to hold it up. But the word represents not just one table, but all tables. So it helps us to think about, by thinking about the concept table, we don't have to worry about all of the individual tables. And humans communicate by exchanging these concepts using words. It's a very important idea. And an interesting feature of concepts is that they're built on the idea of measurement omission. In other words, most measurements don't usually matter. Getting back to our tables example, how many legs there are, the weight of the table, the color, the shape, those kinds of things don't influence the concept of table. Something can be a table regardless of those measured values. A consequence of this is that it means that there's a big gap in human language when it comes to measurement, because measurement omission is a key feature of concepts. It means that there is this big gap. And math is actually the tool that we use to help fill that gap, because it's the science of measurement. So pre-math, in other words, what did we do before math was invented? Since math had to be invented, what happened before then? In everyday life and historically, we often don't need to be exact. And this is the way things were for ages, right? People would talk about a half a glass of water, or about a foot, a pinch of salt, roughly a mile, a few pounds. These kinds of things, this is sort of the everyday sense that most people have of measurement, is that you don't really need to be exact. And this is the way things were before math. There's also an overlap. This overlap of math and language leads to a very interesting and underappreciated skill, which I'm going to talk about a little bit today, and that's estimation. Because we don't have to be exact, we can estimate instead. So what are numbers? We talked about words, a little bit about what words are. Words are concepts. Numbers are actually also concepts that represent measurements. So we can write or communicate these numbers in a bunch of different ways. We can use words, O-N-E for one, for example. We can use digits. We can use our fingers. We can use flashing lights, bits in a computer. Lots of different ways to write and communicate numbers. Historically, the numbers that we have today, we didn't always have those numbers. Again, those had to be invented, and humans went through a few different phases of numerical notation along the way. There was Babylonian and other ancient forms like Roman numbers. There's the modern Arabic form, or Hindu Arabic. And then there are a bunch of different types of numbers, regardless of the notation that we use. There are integers, which include the natural numbers. So natural numbers start at 1 going up, 1, 2, 3, 4, and so on. 0, the concept of 0 actually had to be invented as well. And then negative numbers, -1, -2, and so on. We put those three things together and we have the integers. We have rational numbers. These are the numbers that we can create by using integers in a fraction with a numerator and a denominator. We have real numbers, they can be simple decimals like 0.1 or something like that, or transcendental numbers like the pi that have no repeating patterns in them. And then there's imaginary numbers, so a totally different kind of number based on the foundation of the square root of -1 being an actual valid entity. And think about the numerical notation. What is the history of what numbers used to look like? Here's a couple of different forms. We have the Babylonian ones, which are a part of the cuneiform style language. These are a couple of different symbols that are combined together. You can see that, like for the number 6 or 7, there is a sort of a shape to them, but they also have a count of the number of objects. So there are 7 of those little triangles, and an 8, there are 8 little triangles, 9, and so on. And we get to 10, we invented then a new symbol, and 11 is the 10 plus the 1, and so on. So it's a base 10 kind of a thing. Yeah, a little hard to read when you get up to 59 there at the end, but it was definitely a number system, and an important and useful number system. Then next, Roman numerals. So you may have learned these in school, with the X for 10, C for 100, M for 1,000, and this kind of implicit subtraction, like the number 4 is 5 with a 1 to the left, meaning to subtract it. I guess avoid having to write so many like you did in Babylonian. And we have the ancient Greek symbols, which are different still. So yeah, a lot of different iterations of things before we settled on what we have today. So one interesting feature about some of those older historical numbers is that it's a little bit hard to manage larger numbers. So intellectually, how do we deal with a lot of objects? And one important aspect of that is counting. Counting is a really key aspect to managing larger numbers. And you can think of counting actually as a form of measurement. If you have a bunch of objects in front of you and you want to know how many there are and you count, you're measuring. You're effectively measuring how many of those objects there are. But the important thing to think about here is, why does counting actually help? Why is that a valid, important idea, this counting thing? And it's because the mind has a difficult time dealing with many individual objects at the same time. And so counting allows us to reduce many objects to a single entity, a number. So think about this. Try to observe quantity without counting. Just see a bunch of things in front of you, maybe how many words there are on the screen in front of you, for example. Notice that there's a step that you have to take before determining quantity, and that's classifying the objects that you're interested in. So you'd have to differentiate words from, say, the yellow triangles to the left of each line, or the periods, the punctuation, the dashes, and so on. But now imagine trying to deal with large quantities without being able to use numbers. So there's all these words on the screen. It's like, how do you manage that quantity without a number? It's very difficult. Kids try to sort of work around this by doing math on their fingers. That's their kind of stopgap approach. Kind of a pre-number thing is using fingers to count and manipulate and add and subtract. So what about now getting back to larger numbers? What happens when you try to write larger numbers? These ancient systems, like Roman, there was really only a symbol for up to 1,000. What if you want to write 1,000,000? Do you have to write 1,000 symbols? It would just be untenable. So the modern system that we have today, which is the Hindu-Arabic numbers, they rely on something called the place value notation, and an accompanying concept of 0. So this place value notation solves the large number problem. It allows us to easily write larger numbers. Now, up to a point, if you wanted to write I don't know, a Google, which is you would write 1 with 100 zeros after it, gets to be a little untenable, a little difficult. So there are still problems even with our standard Arabic notation. But getting back to the history now, the development of place value notation was really developed by two Indian mathematicians. Aryabhata developed the place value notation itself in the 5th century, and then Brahmagupta introduced the symbol for zero in the next century after that, in the 6th century. So it's really not that long ago, if you think about it. What's that, 1,500 years or so that we've had these ideas. And note that place value notation actually kind of implies addition. For example, the number 1,234, it's really 1,000 plus 200 plus 30 plus 4. And so that's the genius of the place value notation, is that we can kind of imply those additions and not have to write them out, not have to make them explicit. But they're definitely there. They're embedded in the concept and the idea of a number. So this now brings us to the question of base. And what I mean by that is, what is that? What does the 1 in the digit 10 represent? Is it 1 more than 9, or does it mean something else? For example, Babylonian numbers used base 60, which is it's a handy base because it's the smallest number that's evenly divisible by 2, 3, 4, and 5. And actually, we still use base 60 today, and a form of it, not really explicitly, but a form of it for measuring time. We have 60 seconds per minute, and 60 minutes per hour. And there are other choices other than what we have today, the base 10 that we have today. For example, base 2, which is binary, base 8, which is octal, base 16, which is hexadecimal. There's a few examples there of what that looks like. So they didn't have to settle on base 10, but they did. And of course, the big reason for that is the natural appeal to the connection with that other ancient number system, which is our fingers. And mathematically, from a purely mathematical perspective, base 12 would have actually been pretty nice. Would have been really better than base 10. Base 10 is evenly divisible by 2 and 5, but base 12 is evenly divisible by 2, 3, and 4. So you get, easily get quarters, thirds, and halves kinds of things. But sadly, we don't have that. We have base 10. So again, what does this really mean? Base 10. It tells us in the place value notation what the meaning is of these digits that are next to each other. Does the 1 in 10 actually represents 1 more than 9? It doesn't represent 16, for example, or 60. It means 1 more than 9, 10. Now, for significant digits, so in base 10, this means that each digit is 10 times larger or smaller than the one next to it. So the 1 in 10 is 10 times larger than a 1 by itself. And in everyday human terms, we often really only need the accuracy of a few digits, and we can discard or ignore the rest. So the exact number of digits that we consider significant depends on how we're going to use them. If it's money, for example, we might need a really accurate number. But for many everyday human activities, we don't need that level of accuracy. And it turns out that this is true pretty much regardless of scale. That is, large or small, we often only need to roughly know what the number is. For example, this large number I've written out here, 1,240,652, it takes a long time to say. If one significant digit was good enough, meaning the largest one, we could just simplify that to 1,000,000. A lot easier to say and write and think about. And if we had 2 significant digits, then that would be the first 2, so 1,200,000. For smaller numbers, if we just had a decimal point after the first one, 1 240652. For one significant digit, we could simplify that to just 1 or 1.0. Actually, 1.0 is technically two significant digits, or 1.2 for two significant digits. Now, the law of large numbers. So when you add small numbers to a large one, it turns out that the result is very close to the large one. So a million plus 1 is pretty much a million. In keeping with this use of significant digits, this is an important idea now. This often allows us to ignore small numbers when we're adding a group of numbers that includes large ones. And so this is really just an extension of the idea that we can ignore digits that aren't significant, because place value notation once again implies addition, right? So let's say we wanted to add 1,234,567. We wanted to add 82 and 77 to that. But we only really cared about two significant digits. The answer is 1.2 million. It's basically the first number. The last two additions don't matter. They just don't matter. So this idea, this law of large numbers, can help us dramatically simplify certain types of mathematical operations in our everyday lives. Talk about fraction notation now. So fraction notation is actually, if you think about it, again, this had to be invented. It's a little strange because it contains an implied division and also an implied addition. So for example, 5 and a third, even the language includes it, right? With the and, means 5 plus 1 divided by 3. And even a third, is kind of a language shorthand for 1, right? So it's 5 and meaning plus, meaning 1, third meaning fractional 3. So 5 plus 1 divided by 3, all contained in that sort of compact notation. And this complexity is carried over into performing mathematical operations with these numbers. So we have to kind of, in order to understand and manipulate fractions, we have to know what the notation actually means so that we can break it down and do math on it. Now a little about exponents. Exponents are just a shorthand for multiplying a number by itself. So 4 times 4 times 4 means we're multiplying 4 by itself 3 times, so that's 4 to the third power. Third power, or nx power, whatever, is our language notation for exponents. Regular numbers, that is any old number, can be rewritten by factoring out the number of times that the leftmost digit has to be multiplied by 10. And what I mean by that, here's an example. So we have our 1,234,567. So we can rewrite this number as 1.234567 times 10 to the 6th. And this is important for reasons I'm going to explain in a few moments. But this is a shorthand. And so note that it might seem like longhand here, but it's actually a shorthand. So note that the exponent of 6 here on the number 10, the 10 to the 6th, is just the number of places that we would have to move the decimal point back to the right to get the original number. Or if we're starting with the first number, it's how many places we would have to move the decimal point to the left, starting with it after the 7, or moving it to how many we'd have to move it to the left to get to just having a single digit to its left. So the answer is 6 in both cases. And we can think about square roots and other nth roots as really just fractional exponents. It turns out to be a handy thing from a mathematical perspective. So the square root of 5 is 5 to the 1/2 power, or the cube root of 5 is 5 to the 1/3 power. I'm not going to go into that in any depth, but it's a good thing to know when you're dealing with exponents. So exponents can be used to explicitly write and manage significant digits. This is why it's a very useful and powerful thing to know. For example, with our number from earlier, we can rewrite that. If we had just two significant digits, we could rewrite it as 12.34567 times 10 to the fifth first. And now we can see just taking two significant digits, just those first two numbers would be 12 times 10 to the fifth. We could also say 1.2 times 10 to the sixth, but it turns out that sometimes getting rid of that decimal point entirely simplifies things even further. So an even shorter version of this notation, which is something that you may not have learned in school, I know I didn't, is you take the times 10 part of that 12 times 10 to the fifth, for example, in our example, and we make that implicit and move the exponent to a subscript, and while at the same time adding an explicit sign. So for example, we could rewrite 12 times 10 to the fifth as 12 with a +5 subscript. So I know this is kind of a lot of numbers here, but I'm hoping that the basic concept comes across, that really what I want to get to is this final point, that you can rewrite large numbers or potentially even small numbers as the number, as the significant digits with a subscript saying the exponent when you rewrite it with as a times 10 to the nth sort of a equation. So again, 12 plus 5 means 12 times 10 to the fifth, which is just the same as adding 5 zeros after that 12, right? You can think of the +5 as how many zeros you would write to get back to the significant digit version of that number. So now we're going to take that estimation, we're going to take that exponent notation and use it to do some estimation. So one advantage of working with exponent notation is that it makes multiplication and division so much easier. For multiplication, we can just multiply the significant digits and then add the exponents. Very easy. For division, we just divide the significant digits and subtract the exponents. So this often allows us to transform many digit problems into one or two digit problems that you can do in your head. So for example, if we had 12 plus 5, so that's 12 subscript 5, that's our number from the previous page, and we wanted to multiply that by 300. We can rewrite 300 as 3 with a subscript of +2, because again there are two zeros. Then we just multiply the significant digits, so 12 times 3 is 36, and we add the exponents. 5 plus 2 is 7. So it's 36 plus 7, and we're done. Now we could rewrite that and expand it out as 36 with 7 zeros if we had to. What would that be? 360 million, I think, right? Or another example, taking our 12 plus 5, we want to divide it by that same 300. So this time we would take 12 and divide it by 3 to get 4. And we would take 5 and subtract 2 to get 3. 4 plus 3 is our answer. Another example, this is another type of division, 1 plus 0 this time. So plus 0 means 1 times 10 to the 0. 10 to the 0 is 1. Any number to the 0th power is 1. We want to divide that by 2 plus 3, so that's 2,000. So that would be the 1 divided by 2 is 0.5, and then 0 minus plus 3 is minus 3. And so that's 0.5 to the minus 3. We can simplify that by getting rid of the decimal point as a 5 to the minus 4, 5 times 10 to the minus 4. So note that fractions can often be usefully rewritten as the numerator times the reciprocal of the denominator. This allows us to leverage, that fact allows us to leverage this notation in an even wider range of problems. I would suggest that if this notation doesn't make sense to you kind of intuitively right off the bat, that you, at the end of this lecture, just take a few minutes and think of some sample problems on your own and work through it. When I'm doing math on my own, personal or professional reasons, whatever, I just want to do it on a piece of paper, next to my desk or something. This is the notation that I use because it helps me both simplify and speed up these operations. It also, there's kind of an intuitive, to me anyway, and after thinking about this for quite a long time, there's an intuitive sense of math that this approach kind of imparts. In that you're really only you're minimizing the work that you have to do by leveraging the nature of the structure of the underlying numbers and what they really mean. Now, about the numbers in the world around us. So the truth is that the world is full of numbers, and everything has characteristics that can be measured directly. Height, width, length, weight, volume, speed, rate, shape, everything around you. Just look around you. Everything has got these characteristics. Distances between objects, how many objects there are, grouped in all kinds of ways. And plus, there's in addition to the things that we can measure directly, there's a bunch of things that we can measure indirectly, often by dividing, or perhaps because we need some specialized tooling. Density, acceleration, frequency, for example, can also be measured. Just a side note, this has nothing to do with anything really, but I thought of it while I was writing this, which is a strange use of number in addresses. Have you ever noticed, 123 Main Street or whatever? Those numbers actually aren't counts. They don't, it's not the 123rd house on the block or anything like that. Or there aren't 123, pieces of property in that one lot. It's not a count. It's really just a label. It's kind of a weird use of numbers. And they're there for numerical, they're numerical, they're numbers, because numbers make it easy to order them and to extend them. But we could have just used letters, right? It would have been fine just sorting letters. I think this kind of thing actually is confusing sometimes for kids because it's a different sort of non-intuitive use of numbers that doesn't fit in with the other model that we're used to, or that we really want to use numbers for. The numbers were developed for. So now let's think about addition. So everyone knows how to add, right? We all learned that at a pretty young age, but most of us learned it through rote, through memorization, through a set of rules. Do this, then do this. But it's a funny thing. I've talked to quite a few adults now who don't really have an intuitive understanding of why addition works. They know how to do it, but they don't understand why. Why does it work? So I thought I'd take a few minutes and go over that. So when you're adding long numbers, that is wide numbers with many digits, the way most of us are taught is to first put them in a column. So we have 1, 2, 3, 4 plus 67. Then we add the 7 and the 4, and we carry the 1 and so on. But why does this actually work? Let's think about that for a second. So remember, with our place value notation, 1, 2, 3, 4, 1,234 is actually 1,000. It's even, if you speak the word, the structure of it comes out 1,000 plus 200 plus 30 plus 4, and 67 is 60 plus 7. So what we're really looking for is the sum of all those numbers, right? That's really what we're trying to figure out. So the way we're taught is really a shortcut for the long way. And the long way here, I've kind of spelled it out, and I'll walk through it. So first we would combine the single digits, that is the 7 and the 4, which gives us 11, which is really a 10 and a 1. Then we combine the double digits. We have 30 and 60 and 10, which is 100. Then we combine the triple digits, which are the 200 and the 100. So that gives us 300. And then we merge that using our place value notation back into the final answer, which is 1,301. Now, finally, let's think about a different way to do subtraction. So This is something that I actually use myself whenever I do subtraction, and no one I know of was taught in school this way. Most people are taught the carry method, and I find the carry method to be unintuitive. And so my approach, this is a simple thing. Everyone knows how to subtract, right? Or you can just use a calculator or whatever. But again, this builds on the foundations that we're talking about. So the first thing I want to point out is that A minus B equals C. That is where we're given A and B, and we're given two numbers, and we want to find the third. We can rewrite that as C plus B equals A. So there's only addition now in that second equation. So one way to say that in words is what plus B is equal to A. What plus B is equal to A. So let's take an example here of 523 minus 41. So we start on the right and ask what plus 1 is equal to 3. That answer is 2. That gives us our first digit. Next, what plus 4 is equal to 2? This is our second digit now. It's in the second place. 41, what plus 4 is equal to 2? So the answer there is, of course, nothing. So because 2 is less than 4. So the next part of our process here is we add in an extra 10, and we mark that as a 1 under the 5. And now we say what plus 4 is equal to 12 because we added that extra 10, and the answer is 8. That gives us our next digit. And now we account for that extra 10 that we had, and we say what plus 1, the 1 representing that extra 10, is equal to 5, and the answer is 4, which gives us our final answer, 482, those combining those three digits. So note that in this example, if one significant digit was enough, we could also use the law of large numbers to just estimate the answer at 500, right? 523 is a large number. We're subtracting a small number. We can ignore the small number and just round the big number and get 500, and we're done. So this I call this approach reverse subtraction, and with practice you may find that it's actually quite a bit not only faster but more intuitive than standard subtraction. Now the conclusion. So just reviewing finally, so mathematics is the science of measurement. Numbers and notation are the language we use in that science. Numbers are structured in a carefully designed way that has actually evolved over time. Estimation can be a useful way to simplify math, and one way of approaching estimation is the law of large numbers, where significant digits and exponents are powerful tools. And exponents can also be used to simplify multiplication and division. And finally, thinking about subtraction as reverse addition can help make subtraction easier, faster, and more intuitive. That's it for this lecture. Thank you very much.